Uh, Thank you all for coming to my presentation. As introduced, I'm James, and I'll be presenting my work, which makes the following contributions. I introduce a novel approach for generating programs and verifying their dynamic behavior. I use this approach to enable the generation and verification of C code in Agda. I re-implement and verify the Stromonis streams library, and I show that this re-implementation achieves a 4 to 140 times speedup compared to a similar library. So I'll first give a brief overview of some background material, and then I'll introduce the approach, and then finally I'll discuss the streams library. Generative metaprogramming is the construction of programs that produce other programs. Typically, a generating program specializes the generated program for a particular instance of a problem that can enable faster and more efficient computation than a general purpose implementation. This is illustrated on the slide. Normal programming is represented at the top of the slide. Your program is run and generates some output. A generative metaprogram with 2 stages is run to produce a new program. This generated program is then run to produce some output. Staging is a common form of generative metaprogramming, which allows for the manipulation of quoted code as data. Quoted code appears inline in the generator. The example on this slide contrasts a normal implementation of the power function and a staged implementation using MetaOCaml, a state-of-the-art staged language based on OCaml. The normal implementation at the top of the slide calculates the nth power of x by multiplying by the nth minus 1th power of x by x, where x to the 0 is 1. The staged implementation, S-power, takes a similar approach, but generates code specialized for when the exponent is known when the code is generated. In S-power, angle brackets surround quoted code, and tildes embed code snippets in quoted code. You can think of this as switching between execute later with angle brackets and execute now with tilde. The important thing to notice here is that the evaluation of the if statement occurs at staging time when the code is generated, rather than at runtime, improving the performance over the normal power function at the top of the slide. Even from this simple example, hopefully you can see that staging can be quite useful. Unfortunately, existing state-of-the-art languages, such as MetaOCaml, have 2 key limitations. Firstly, existing languages only make guarantees of the static semantics of generated programs and not of the dynamic semantics. For example, MetaOCaml will check that our generated code is well typed, but it cannot make any guarantees of the runtime behavior of the generated program. This can make the generated program difficult to debug because any issues are caused indirectly by the code of the generator. Secondly, many existing languages generate programs in the language of the generator, but most languages are not well suited to both tasks. High-level languages make code generators easy to write, whereas performant low-level languages are often better targets. My work overcomes both of these limitations by using heterogeneous staging, which allows the host and target language to be different, unlike in a homogeneous multi-stage languages such as MetaOCaml. A heterogeneous approach allows the generating language to become expressive enough to capture dynamic behavior of the target, while the low-level target language may have desirable performance properties. This slide illustrates how this comes together in my approach to enable verified heterogeneous staging. My approach consists of 4 components that are implemented in the host language. Firstly, in the top left is the target language specification, which details the syntactic constructs of the target language. Next, in the top right, we encode the dynamic behavior of the target language in semantic models. My approach supports and also encourages the specification of multiple semantic models, so that the user may make use of the most appropriate semantics for their purpose. Along the bottom of the slide, the figure represents how the user can make use of the target language. In the bottom left are user generators, which can be written in style similar to existing systems. If they don't want to, the user can ignore the dynamic guarantees provided by the semantic models and achieve identical behavior to current state-of-the-art systems. If they do want to prove dynamic properties of their generated code, then they can employ one or more semantic models. To illustrate my approach, I enable C code to be generated from Agda and then re-implement the state-of-the-art Stromonas stage streams library with this embedding of C. The correctness of Stromonas is then proven based on an encoding of the composite semantics of C. Starting with the embedding of C and its semantics. My work embeds a subset of the C programming language in Agda. The subset doesn't include dynamic memory allocation, but is expressive enough to implement the Stromonas library and the stage power function that we saw previously. The semantics are encoded as axioms in Agda and are based on the well-studied composite semantics. From these axioms, I define the equivalence of potentially non-terminating programs and prove useful lemmas such as beta and eta equivalences. The Stromonas library uses staging to push many of the abstraction overheads in stream processing to the generator, much like we saw in the power function example previously. I prove the correctness of my re-implementation using the composite semantics for C and by defining an equivalence between streams. Two streams are equivalent if the program generated for all folds over the streams are equivalent. With this definition, I prove several equivalences and sketch proofs for many more. For example, I prove that the map function is distributive over function composition, that mapping the identity function over the stream leaves the stream unchanged, and that filtering a stream with a constant true function gives the same stream back. Finally, I tested the performance of my stage streams library. I tested my approach against the Stream Fusion Haskell library in a common set of benchmarks. As shown in this plot, my implementation achieves 4 to 140 times speed up compared to the Haskell library. In summary, my work presents a novel approach to the verification of generated code. I've illustrated this approach by writing a streams library that generates high-performing C code from Agda and mechanically proves the correctness of the generated code. Thank you all for listening.
Thank you, James. Let's see. Okay, Jesper, can you unmute yourself and ask your question?
Yeah, sure. Yeah, thanks for the talk. It's very interesting work. Yeah, so my question is, you say you have a model of the C language similar to a composite model. I was wondering if this is something that can be reused as well for other things. I was thinking, for example, of doing verified optimizations on the code you generate or something like that. Yeah,
that's exactly the purpose. So the Stromonas library does a similar kind of thing where it takes these abstract streams and performs kind of loop fusion, which is a form of optimization.
Right.
And we prove the correctness of that transformation.
Okay, yeah. But it's not, your model of C is not specific to the thing that you're doing. Or...
Correct, yeah. It's a general model,
cool.
As the composite work is.
Yeah, very nice. Yeah.
Thanks for your question.
Okay. Any other questions? No?
Sorry, I do have a question.
Yes, please.
Right. So maybe I'm missing something, but somehow I feel that your work looks more like a some kind of verified compiler that in which you use a DSL to write some high-level functional program, which is then sort of compiled to efficient C code. So I guess my question is more like, I don't really see the kind of staging you do in your powers example where you have quotes and unquotes and that kind of code manipulating stuff. Can you sort of show a concrete example, for example, to sort of clarify this point?
Sure. Thank you for your question. I don't have a concrete example on the slide. I thought showing code would be a bit confusing. I can link you to my repository, which has this kind of quoting, unquoting annotation. But the example you saw on the slide of the stage power function in MetaOCaml is very similar to the kind of, that is almost a DSL in OCaml, And I've implemented a very similar thing in Actor 4C. Does that answer your question?
Right, okay. So apparently I need to look into your repository and find a few examples for myself.
Yeah, I'm happy to discuss this further if you'd like, either here or offline.
Right, thank you.
No worries.
Okay. Any more questions? So can you tell me a bit more about your C fragment? Like what kind of programs we can write?
Of course. Thanks for your question. So this is one of the areas where I think there's the most potential for further work and further development. Currently, the C fragment is quite limited, but as I mentioned during my presentation, it's able to implement firstly the stage power function, which is a fairly simple program, but also these stream computations, which are less simple. And even though the fragment of C is quite small, you can still have both terminating and non-terminating programs. The only limitation, or kind of the main limitation, is no dynamic memory allocation. And so that includes kind of dynamic functions and higher order functions.
Okay, thanks.
Thank you for your question. I will cede my screen share.
Yes, so if there's no more question, then let's thank James for the talk.